This is the second segment of Module 3. In this case, we're going to talk about the measures of central tendency, which corresponds to section 3.1 in the textbook. Before we start, in the formulas that follow for measures of central tendency and dispersion, we're going to use the following letters. So if you see capital N, that designates a population size, that is the number of values in the population. If you see a lowercase n, that designates the sample size, which is the number of values in the sample. The letter X designates the variable. For example, X could be the weight in kilograms. And this sum of X, this letter is called the capital sigma letter in the Greek alphabet. It's like the mark of the Zorro, if you remember that movie. So he goes like this. Well, in this case, we go like this. So if the Zorro were a statistician, he will sign everything with that letter, because we use that letter a lot in statistics. And that capital sigma X, that indicates that you sum all the values of X. Here's an example. The values of the variable X are, in this case, 5, 4, 7, and 3. So if you write sigma, capital sigma of X, that means sum the values of X. So you will sum 5 plus 4 plus 7 plus 3. And if you carry out that calculation, you will obtain 19. So this is the letters that we're going to use in the formulas that follow. So if you have a question about those formulas, come back here and see what each symbol represents. All right, the first measure of centrality, and the one that you're probably most familiar with, is the mean. So again, this is a measure of central tendency calculated from the values in the sample or in the population. Physically, it represents the center of gravity of the frequency distribution. So I put this little diagram here where you have the frequency distribution balanced on a plank, rather put on a plank, and then you use the fulcrum, and you move this fulcrum around until the whole thing is balanced on the tip of the fulcrum. That point where this thing balances, that will be the position of the mean of the data in the sample or in the population. The way we calculate the mean is you simply sum all the values and divide it by the number of values. So if you're calculating the population mean, mu, then you will sum all the values in the population and divide it by all the values in the population, capital M. If you're calculating the sample mean, x bar, then you will sum the observations in the sample and divide it by the number of values in the sample. So I think you're familiar with this, so let's look at an example. In this example, the speed of 8 cars traveling on a highway were measured in miles per hour. The speeds that were recorded are 77, 82, 74, 81, 79, 84, 74, and 78. So we want to calculate the mean of the speed or the average speed. And you will see we'll use mean and average as equivalent things. And in here, the mean that we're talking about is called the arithmetic mean, or the arithmetic mean. All right, so let's do that. So again, the variable here is the speed of cars in miles per hour. The values of the variable are here, the same that we saw on the previous slide. There are 8 values in the sample, so lower n is 8. And so we calculate the mean using our formula, which says sum the values of x divided by the number of values, which is 8. And if you carry out this calculation, you obtain 78.625. So we say that the average speed of the 8 cars is 78.625 miles per hour. And this brings an important point that I've been forgetting to remind you. Make sure that you have a calculator with yourself at all times, because you're going to be required to do some calculations in the homeworks, the quizzes, and the exams. And a simple calculator is fine. I have this old TI 30XA, and it works fine for everything that I do here. So again, whatever calculator you have, just be mindful that the telephone calculator is not going to be allowed during the exams. So I recommend that you use your calculator and learn to use your calculator so that you don't have any problems during the exams. All right, so the next measure of centrality is the median. The median, again, is a measure of centrality, measure of central tendency based on the position of the ranked data. So what do we mean by ranked data? Well, that means that we need to order all the values in the sample or in the population from the smallest to the largest. And second, we assign a rank to each of these values. Then once you have the ranked data, then the median is a data value that is equal to the middle rank, so that 50% of the ranked values are below the median and 50% of the values are above the median. Let's look at an example, or rather the procedure to obtain the median. So the very first step is to rank the values from smallest to largest. The second step is assign a rank to each value and then calculate the middle rank using this formula. So the first formula is if you're using the population, so it's the number of observations, the population plus 1 divided by 2. Or if you're using the number of values in the sample, then it'd be lowercase n plus 1 divided by 2. Then the median is the data value that corresponds to the calculated middle rank. Let's look at an example. So in this case, this is the first example, we have the variable x has 5 values. So it's an odd number of values, and the lowercase n is an odd number. So the first step, we rank the values from smallest to largest. So you look at the data and you see that 29 is the smallest, then it's followed by 31, then by 35, then 39 and 39. So you put that here in order from smallest to largest. Then you assign a rank. The rank means 1, 2, 3, 4, 5, 6, and so on. Then you calculate the middle rank. So n is 5 plus 1 is 6 divided by 2 is 3. That means that the median is a value with a rank of 3. So you look at the rank of 3 right here, and you see that the corresponding value is 35. So the median, x tilde, because this is a sample, is x tilde. This is 35. So here's another example. Now in this case, it's the same data as in the previous example, except that we added one more value, so that we have that, so that the number of values in the sample is an even number. So now the same thing, we order the data from the data values in the sample from smallest to largest, and we assign them a rank. Then we calculate the middle rank. In this case, is n is 6 plus 1 is 7 divided by 2 is 3.5. That means that the median is right in the middle between the third rank and the fourth rank observation. So to get the middle, what we do is we sum this value plus that value and divide it by 2. So in other words, we're taking the average of these two adjacent ranks. And so the median, x tilde, because this is a sample, is 37. So with these two examples, I'm illustrating the two typical cases when you are trying to find the mean. In one case, if you have an odd number of observations in your sample, the middle rank is going to be one specific value, and so the median is pretty easy to find. If you have an odd number of values, you're going to end up taking an average of the two central ranked values. All right, so here's another example. This is an example of 7 12-year-old boys who were weighed in pounds. The weights are right here, and they're asking us to find the median of these 7 boys. All right, so as before, the first step, rank the values from smallest to largest, and then you assign a rank to each of them. Then you compute the middle rank. So the number of observations here is 7, plus 1 is 8, divided by 2 is 4. So the median is the value at rank 4, right here, 90. And now you notice that in here, we're not paying attention as to how big or how small these numbers are. All we're doing is ordering them and using their position in the ranked sequence of values to determine what is the middle value. So here the median is 90, so we have 50% of the observations above it and 50% of the observations below it. So again, that's how the median works. All right, another important aspect that we need to talk about is what we call an outlier. An outlier is just simply an observation that is very large or very small compared to the other observations. So here's an example of speeds measured in miles per hour of cars traveling on a highway. So here the question is, are there any outliers in this data? And if you scan the data, you right away you see that this car was traveling very, very slowly, whereas this car was driving really, really fast. So I will say that there appear to be two outliers in this data set. 35, which is very different from the majority of the values, and 115. Now in practice, whenever we see this, you always go and investigate what is the source of this data, because someone may have made a mistake, or someone was using the wrong instrument, or you find an issue. Maybe this guy or this lady, whoever, or the driver, let's say, maybe was distracted with the telephone, or maybe experienced some mechanical failure. Whereas this guy, maybe he was running again away from a problem, say. All right, so but always investigate why these numbers appear, because you're going to find interesting things when you do that. All right, so how does an outlier affect the mean or the median? So here's the same data set that we had before in example 1 with 5 values. And again, if you find the median, we found that it's been 35. If you calculate the mean, you sum all the values, divide by 5. If you do that, you find that the median is 34.6. Now let's assume that the value was not 39, but rather 390. So this will be definitely an outlier. Now look at what happens at the median. Again, we're not paying attention to the magnitude of the values. We only paying attention to where what is the position of the values in the rank order. So the median does not change at all. But look at what happens to the mean. This number really increases the summation of these values divided by 5. And look at what happened to the mean. Is about almost 3 times as big as this, just because of these outliers. So keep in mind that outliers greatly affect the mean, but they really don't impact the median. So the median is a more appropriate measure of centrality when there are true outliers in the data. True meaning that this number, for example, 390, is a correct measure. I don't know what they're measuring here, but we went and verified, and sure enough, that is a real value. So when that is the case, the mean is not the best measure of centrality. You will use the median. All right, the last measure of location is the mode, and that corresponds to the most frequent value or values in the data set. Now here are 3 examples. So if you look at this data and you scan it, you look at which data appear more frequently. And if you scan it, then you see that there is 74 appears twice. So the mode of this data set will be 74. If you scan this data, you're going to find that none of the values repeat. That means that this data set does not have a mode. If you look at the age of the students, then you will see that there are multiple modes. There is 19 appears twice, 21 appears twice, and 22 appears twice. So this data set has 3 modes. So data set do not always have a unique mode. You may have multiple modes, 1 mode, or no modes. And that's the main reason why the mode is not used in general for statistical analysis. Although the mode is often used for qualitative data. Like in this example, we have the grades of 10 students. This is the example I used in chapter 2. So what is the mode of this data set? Well, and this is a qualitative variable. And you see that the letter C, the grade C, is the one that repeats the more often. So the mode of the grades of these students in this exam is C. So again, we're not going to use this measure of centrality because it's not unique to a data set. And so from now on, we're going to talk about the mode and the mean as the measures of centrality. I'm sorry, the mean and the median as the measures of centrality. All right, in the next segment, we'll talk about these comparisons of the mean and the median.